You're listening to Wurth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, sensor technology, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. Today, we're taking a look at trends in temperature measurement. We're also going to look at the different technology approaches of temperature sensors. We want to focus on silicon-based temperature sensors with a digital interface. So by doing this, we'll show essential features of the temperature sensor, and we're specifically going to look at the WSEN-TIDS from Wurth Electronic. Finally, we'll discuss advantages of these sensor types, especially in Industry 4.0 and IIoT applications, and we'll wrap it up with a discussion on optimization options for the broad design to meet different application requirements.
So let's go briefly to the agenda for today's webinar. First, I will explain about the types of the temperature sensors and the sensors which are needed today in the Industry 4.0 and the need of digitalization. Then we'll look at the WSEN-TIDS, the digital temperature sensors from the Würth Elektronik, and some of the applications of these sensors and some of the design recommendations from our side so that you can have a perfect application and get the most out of the temperature sensors. So the temperature sensors, they are nowadays coming in so many different types, some of which you already know. The basic and which are the most widely used in the wide temperature ranges are the thermocouples. They are used from minus 250 degrees to more than 1000 degrees. The thermocouples are nothing but two different type of metal. They are tied together, and because of the Seebeck effect, they conduct the thermal conductivity is different, and so that they produce some uh, millivolt outputs that can be directly linked to the temperature. Basically, the thermocouple uses a reference temperature as a cold junction, and the hot junction is the temperature where you measure with respect to the temperature of the cold junction. On the other hand, these kind of sensors are highly nonlinear. Also, they are not stable and the accuracy is not so good. But the fact is that they can be used from a wide range of temperature. The next ones are the RTD. These are widely known as the PT100, PT1000 ones. You must be knowing them from the cylindrical types, or nowadays they are also available in SMD types. They are very high accurate and they are also linear. But on the other hand, they are highly expensive. So very high accuracy also comes at the cost of price. Next is the NTC PTC thermistors. These are nothing but only the passive components on your PCBs. The current is passed through the resistors, and the current is being monitored based on the temperature, and that changes with the temperature increases or decreases. So NTC has a negative temperature coefficient and PTC has the positive temperature coefficient. These kind of thermistors have a self-heating problem, so that you have to recalibrate it when the temperature is being changed. Also, in the dynamic temperature where your temperature is changing very fast, these kind of temperature sensors are not recommended. Also, these are very extremely non-linear, so you have to again scale based on your application. Next is the silicon-based silicon semiconductor-based sensors, which are the topic for today's webinar. And they also have the similar measurement range of the thermistors, a little bit smaller, from minus 55 to 140 degrees approximately. They basically work on the intrinsic property of the silicon band gap. So the forward voltage of a diode is directly linked to the temperature, and this is where the simple property of the semiconductor can be realized as a temperature sensor. Here is the comparison of all of the temperature sensors what I discussed in the previous slide. You can see that, for example, the thermocouple, their accuracy is limited because they require cold junction compensation, which is the knowing the temperature of your cold junction. So your reference temperature limits your accuracy at the end. On the other hand, the RTDs have the highest of the accuracy. Also, the semiconductor based sensor also can be now reached up to a very high accuracy. The linearity, as you can see, the thermistor and thermocouple are very non-linear. On the other hand, the semiconductor based sensors are very much linear. A very important point is that what peripheral or circuits or calibration do you require when you use these kind of sensors? For thermocouples, as you see that as we discussed, that you need the cold junction compensation, you also need the amplification of the millivolt output, and then you have to scale. Sometimes you also need, when you need the digital output, then you also need an ADC converter. Same way for the RTD, you have to do scaling. Thermistor, the same thing, that you have to do scaling, and you need calibration for more than 1 points, which can be time consuming as well. On the other hand, semiconductor based sensors are usually fully calibrated so that you don't have to calibrate it once you place it on your PCB or once you design it. The footprint wise, the semiconductor based sensors are the smallest. They can be also comparable in the size of thermistors, and nowadays some of the RTDs also come in the same footprints. Before we move forward, let me explain something about the Industry 4.0 or the industrial IoT, what has been developing these days. Basically, the all of the industrial equipments are getting more and more interconnected. More and more process automatization has been happening, and the machinery needs to work on their own. They send data wirelessly to a sensor node. You need remote access. You also need to monitor and control your machines or your data remotely, and also do predictive maintenance if your machine needs some correction or it is going to uh, malfunction or not, that you can read from the sensor data. So wireless connectivity and digitalization is at the basis of the industry 4.0. On the other hand, temperature is also one of the most measured environmental quantity. So many physical chemical properties depend on the temperature, and that's why temperature needs to be measured more often. Some of the examples where industry 4.0 is linked to temperature sensors. For example, crop monitoring or livestock monitoring, where in the fields some crop needs some water or some um animals are not feeling well or they are not in the full shape or they need some medical attention. Smart clothes, for example, firefighters nowadays have temperature sensor integrated in their jacket. They monitor the ambient temperature and also the body temperature. Cold chain monitoring in the food industry and home appliances, of course, they are getting more and more wireless these days, and they are getting interconnected more and more. So in order to realize this kind of system, what do you need at the end? You need a sensor which is digital, that you can send your data wirelessly to a sensor node or your base station easily. It should be flexible. It can be used from it can be it can be changed in the functionality from the software. For example, you can change the data rate, you can have some interrupts. Of course, it should be battery driven for the remote or mobile applications, and it should consume very less power. And also, nowadays the devices are becoming more and more smaller, so the sensor should also be compact. Here is an example of a cold chain monitoring in the food industry, from where the product is manufactured in certain environments and it is also transported and then stored in certain conditions so that it doesn't go bad or some microorganisms doesn't get to start evolving in the food. And these things must also be taken care from the production to the plate, and the production to the plate is not a small journey. It takes sometimes takes lots and lots of days and goes through different means of transport. what do you need for these kind of food industry and with this kind of logistic supply chain? You need real-time monitoring. You monitor your food if it's at the correct temperature throughout the journey. You need to have some data logging also, so that for liability issues, for example, if and when you know that the food might have gone wrong, so that you cannot process it any further, or you cannot sell it to a consumer. It should be battery operated. Most of the time the supply chain, the food is traveling in trucks or in airplanes, and it should also have a fast response time, so that it can react very quickly to the temperature changes and alert a user that please pay attention, the temperature is not correct, for example. Here is an example of how a complete system for a cold chain monitoring could look like. So here you have a temperature sensor which continuously monitors the food and send food temperature, and then it sends the data to the microcontroller, which is also has GNSS module which can also track your location, and everything data is all of the data is transported to a base station or a sensor node through a RF module, which can use either Wi-Fi, Bluetooth, or any other proprietary solutions. So at the end, it's this requires also more sensors than temperature sensors, but here we are just talking about the temperature sensor. So at the end, you need a sensor that measures the temperature digitally in order to send the data directly to the server or log directly in the digital form without any further processing. Coming back to the temperature sensors, which are silicon based, how do they work? So as mentioned, that forward voltage of the silicon diode is temperature dependent. So this diode is basically the base emitter junction of an bipolar junction transistor. Here you can see the forward voltage is dependent of forward voltage of the BJT is dependent on so many other temperatures. But if we take two different transistors and supply them with different currents, then we can have the difference of the forward voltages, which is only dependent on the temperature, and the equation becomes much more simpler. So as you see, the forward voltage is directly proportional to the temperature and has the very linear output. So very simple phenomena leads to realization of a complete temperature sensor. This forward voltage is then amplified, then digitalized, and calibration is then performed in the next steps. That brings us to the digital temperature sensor from the Würth Elektronik, the WSEN-TIDS. What do we have in this sensor? So as mentioned, we have the same sensing element, diode. The forward voltage is then amplified. It has an onboard amplifier. Then it is digitalized by ADC converter, and then signal processing is done on chip. The digital temperature value is then stored in the inbuilt temperature registers, and there are also control registers where the calibration data is stored. There is also a dedicated control logic and digital comparator where the user can store his own temperature, and the measured temperature is then compared with the user defined temperature in order to generate an interrupt. The temperature registers are easily connected, can be easily read from the I2C serial digital interface. That two-wire interface you can connect directly to your microcontroller. So at the end, the whole sensing element, the analog front end and the digital front end is all combined in one single IC. This whole sensor is fully factory calibrated, so no application specific calibration is required from the application side or from the user side. On the other end, you also don't need any peripheral circuits that you need usually for some of the analog sensors. For example, you need a separate amplifier, separate digital converter, or some filters. And here, that requirement that is not needed, and that makes your end application circuit designing much simpler. Let's have a look at some of the parameters. As mentioned, it has a I2C interface and two different I2C addresses are available so that you can connect two sensors on the same I2C bus. The measurement range is from -40 degrees to 125 degrees. For the current IoT and industrial application, this measurement range is more than adequate. It has 16-bit digital output resolution. The typical accuracy is 0.25 degrees between -10 and 60 degrees, and overall accuracy is 0.7 degrees. As mentioned, this also has a very low current consumption and operates between 1.5 to 3.6 degrees, so that perfectly suitable for the battery operated devices. Uh, Also, it's a 6-pin SMD device, can be easily mounted on the PCB, and there is also a exposed pad at the bottom so that the temperature sensing with the environment has better connection. Here is a typical curve of the accuracy of the temperature sensor, which was measured in our labs from -40 to 125 degrees, where you see the accuracy between -10 and 60 degrees is better 0.25 degrees, and where you see the measured temperature curve in this temperature range as well. Let's look at some of the features and mode of the sensors. Here you see the block diagram. So basically, when you power up the temperature sensor, it is always in the power down mode. In the power down mode, it consumes the least amount of power, and in certain applications, the sensor remains most of the time in the power down mode. The first is the single conversion mode, where a user gives an input that he needs to read one temperature reading via microcontroller. So one temperature measurement is measured from the sensing element and converted digitalized and stored in the I2C, stored in the internal registers, and user can read this data through microcontroller. After this conversion, the sensor again moves back to the power down mode. On the other hand, there is also continuous mode where you can select your data rates from 25 Hz to 200 Hz. That means from 25 Hz, you get as many as 25 samples in a second, to 200 Hz, it's 200 samples per second. And in continuous mode, the sensor continuously measures a new temperature data as per the defined data rate. For sure, this consumes more power than the single conversion mode. Also, there is user-defined temperature thresholds that you can set from the user side that generates an interrupt. For example, when you set the temperature limit high and low, if the temperature goes above it, the interrupt goes low, so it's active low interrupt, and the microcontroller side it is notified that the temperature is high or low. Some steps should be taken, or microcontroller or the host controller has to notify the sensor that acknowledge the alert, and then the alert goes again to active high. It waits then again for another event for the temperature high or low, and then again the interrupt is enabled. Let's move forward to some of the applications in industry where the temperature sensors can be used. Um, the very first is the cool junction compensation in the thermocouple. So as mentioned previously that the thermocouple uses two different metals connected together, and the cold junction is the reference temperature which with respect to the target temperature is measured. Usually the thermocouples have then some filters, some amplifier, and the uh, digital circuit that stores the temperature in a microcontroller. In order to know the cold junction of the sensor, most widely used sensors are the RTD, platinum-based RTD sensors, where you place the RTD as close as to the cold junction. Then the RTD circuit also uses some amplifier, some ADC converter, and then you have some data logs that compare the temperature from the thermocouple and the RTD, and then you have the temperature of the cold junction. So here, when you say that my sensor has accuracy of X percentage, then you add also some peripheral devices, for example, filters, amplifiers, which also add some noise and also adds inaccuracy of your complete system. So at the end, sometimes you also have to again recalibrate your whole system. The RTDs also might have problem of self-heating, and they are also very design sensitive. So you have to take care of your design and invest a lot of time designing complex circuits. A solution that we propose would be that use a digital temperature sensor for the cold junction compensation, so that you have a directly digital output from the sensor that can be directly fed to the microcontroller and compare it with your thermocouple circuits. This eliminates need of your all the peripheral components that you need and also makes your layout very simple. Here, one point is also very important, that you are comparing a system accuracy versus a device accuracy. So system accuracy means that you have RTD, you have your analog filters, and then you have your ADC, and this whole uh, accuracy is called the whole system accuracy. On the other hand, the whole sensor, being one single IC, comes fully calibrated and pre-calibrated. Same way, you have to sometimes perform, as mentioned, the whole system's calibration. For that, the whole system needs to be kept at one single temperature. This could be tricky in some of the applications. Another application for the temperature monitoring and control is in the laptops, that we have a automatic fan control. So we have a temperature sensor on chip on the PCB, which sends the data to microcontroller, and based on the temperature alert system or interrupt, it sends this data to it, drives the some actuator or fan to drive to run at certain speed or to shut down when the temperature is not so high. Also, in some of the remote application, this data is sent to a wireless module, and remote host can also control the fan speed based on the temperature. This kind of temperature monitoring is today in DRAMs, in the power supplies, or also you can see in the computer main board, where the temperature of the PCB or the whole housing needs to be maintained at certain point. Another example is the temperature monitoring of the server room. This is a picture of a server room from our Germany office, where we put a temperature sensor in the server room, because server room needs to be continuously monitored at certain temperature. The temperature should not be higher at some point, and this is the uh, logging station or the display station at our working desk, that we can constantly monitor the temperature of the server room wirelessly. Some of the other applications include the temperature compensation for gas sensors, for thermocouple, as we already saw in the previous slides. Asset tracking, not just the food tracking, but also some of the other supply chain needs to track the temperature as well. The servers and server rooms, in the HVAC applications, where the air temperature needs to be monitored in the ducts. In the house, the thermostat, we are having more and more digital devices to control the temperature of the house, and of course the white goods, refrigerators, microwaves needs temperature sensors to work at a certain temperature. And these all sensors nowadays require a digital sensor that can be fed, that can be implemented very easily and very quickly. The last part of the today's webinar is the design recommendation for this sensor. As mentioned, that the sensor has a bottom pad which is exposed. This bottom pad is a die attach pad, where the sensor die or the sensor die is placed. So the best thermal conduction path is realized from bottom to top, and you can have a very accurate junction temperature. And this is one of the benefit of the sensor. So in the first example, if you want to measure the ambient temperature, so for the ambient temperature, the sensor placement is also key. For example, you need to place your heat source IC as far as possible from the sensor. Also, it can be realized from some perforation or an island cutout or some slits that it has more airflow so that air can flow easily to the sensor. Also, the ground plane is most common thermal conductive element in the whole PCB. So the sensor should be placed outside the whole ground plane, and also the hashed ground plane also helps in thermal conductivity. On the other hand, if you want to measure the component temperature, here you need to place the temperature sensor as close as possible to the heat source IC. Also, you can connect the ground plane of the heat source IC to the central pad of the sensor so that a heat conduction path has been generated. You can also place the temperature sensor on the other side of the IC and then directly have the connection from the ground plane to the central pad. This will have the shortest thermal conduction path for the PCB, as PCB are approximately 1.6 millimeters thick, and this will have a very high temperature of your temperature monitoring of your target device. Here we also did some similar kind of experiment where we had a hole cut on the bottom side of the PCB so that the pad was exposed to the air, and on the second PCB we had the central pad attached to the ground plane, and then we measured the temperature rise and fall time. So the red curve is the temperature measurement of the air with the PCB with the hole, and the gray curve is the PCB with the pad attached, temperature central pad attached to the ground. As you can see that the ambient sensor has a very slightly higher response time than the PCB pad, so that this senses the ambient temperature faster and responds to the temperature change faster than the PCB. The response time was almost approximately 7 seconds faster. So these kind of design consideration are very important where your application needs which kind of design, whether you want to measure an ambient temperature, or whether you want to measure some PCB temperature or a target device temperature, or even in small confined area where you have to measure some temperature of a smaller area where you can also use the temperature sensor. That brings us to the end of the temperature sensor presentation. In the last slide, I would like to summarize what we have discussed. So what do we offer is that improved efficiency, because the sensor is fully calibrated. You don't have to calibrate it as per your application. The ease of integration, you don't need any peripheral circuits or analog circuits. You can directly place the sensor and design in the sensor in your PCB. The sensor is robust in operation. It is qualified with different accelerated tests. And as mentioned, it is Industry 4.0 compatible. It can be operated for battery operated devices, and also it has very low current consumption. At the end, what do we offer as well is the long time availability of these sensors. So if you design in, the sensor will be available for a longer time, which is industry standard. All the sensors are available ex stock. We also offer direct design-in support and technical support. The user manuals and app notes are available as well. The CAD and EDA libraries for the sensors are also available. For the quick prototyping, you can also use the evaluation board. For the evaluation board, we also offer the software development kit, where we have some example codes that you can directly use this as a first communication of the sensor with your microcontroller.
As with all of our podcasts, some images and videos will be unavailable based on the streaming service. You can access all videos and images by simply clicking on the link provided in the description or copy and paste it into a web browser or visit the Wurth Elektronik YouTube page. You can also find the entire lineup of wireless connectivity and sensors for your applications by visiting Wurth Elektronik online. These include temperature, humidity with integrated temperature, 6-axis IMU, 3-axis acceleration, absolute and differential pressure sensors, along with evaluation kits and related components to complete your design. You are listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast.